Hey everybody, welcome back. Today we're going to talk a little bit more about temperature units, Celsius and Kelvin. We're going to talk about how to convert units of volume, and we're going to talk about Jimbo's Big Block, a muscle car, 454 cubic inches. Then we're going to talk about how you don't always need to know a formula or memorize it because the units always got your back. Let's go to work. Hola everyone, hola, ¿qué tal? Mike here, and we're going to talk a little bit more about units today and handling units. And we left off last time having not talked about temperature. You will never see a temperature in Fahrenheit except on the weather or if you drive by a bank sign or something like that. But in science we have the more sort of useful units of Celsius, because if you're familiar with Celsius, you know that there's two landmarks. They're not quite perfectly power of 10 related, but they're by hundreds, which we also like. Humans like hundreds. And that is, of course, the freezing point of water is at 0 degrees C, and the boiling point of water is at 100 degrees C. There's a problem with that scale, though. It is not what we call absolute, meaning 0 doesn't mean 0. So let's think about what temperature really is. It's a measure of kinetic energy, which is a manifestation of heat, right? So what happens is we're not at 0 heat or 0 kinetic energy at 0 degrees Celsius. They just figured, hey, we'll make it all around water because our planet is covered with water, 2/3 of it, 3/4 of it, however much. So what we do is we found another scale. So I'm going to tell you the story of absolute 0. Let's say here's temperature, and actually we do an experiment like this in General Chemistry 1. So temperature increasing. Let's say this is guys, temperature's over here. Goofball Mike got it wrong. Let's say this is molecular motion on the x-axis or the y-axis. Actually, we'll talk about the experiment we do. Let's say this is pressure of a balloon, or not even a balloon. You go and you take a sample of gas, and you were to watch its pressure change as you cool it down. So then you'd have some sort of graph that would have a shape sort of linear. In other words, here we are. Let's say this is room temperature, 25 degrees C. And here we are. Who cares what the value is, but I'll just take it from me. If you were to keep going down and down and down, and we'll call this this would be 0 degrees C. The pressure would go down linearly. So that would make a line. And if you were to keep going now, you'd have to freeze it, and you take the gas and put it in the freezer, and then you go take and put it in dry ice, and then you go, and maybe even my slope is too abrupt. It should be a lesser slope, but I'd go off the page. There'd be a point where and you wouldn't go past it, where the pressure would be 0 because all molecular motion comes to a halt. And that is what we call absolute. Remember the absolute scale? 0. Not vodka. 0. That is minus 273 degrees C. And so with Kelvin, what we do is we call that 0 kelvins. They don't say degrees Kelvin. They don't say degrees Kelvin. They just call them kelvins. And so you see, if 0 Kelvin is negative 273, the only thing you got to remember are two things. Remember, I don't like it when you memorize stuff just surface level because you get them wrong. Just remember that Kelvin is absolute, and an absolute scale can never be 0. What's another example of an absolute scale? Your mass. You can't step on a scale and say, oh man, I weighed negative 10 pounds. You don't weigh negative 10 pounds. You obviously weigh something. And the least you could weigh is 0. So you can't have negative mass. You can't have negative Kelvin temperatures. And so that's an example of an absolute scale. So all you got to remember is that magic number 273, and then you say, geez, what do I do? Do I add or do I subtract? Well, you go and you recreate this, and you say, maybe you do the wrong thing. You say, I'm going to go ahead and subtract from 273, and then you'd be like, oh, I can't do that, because that would make Kelvin negative, and Kelvins are never negative. So this would be 273 Kelvin. And therefore, at 100 degrees, you see what you're doing, you'd have to add to go from Celsius to Kelvin, 373. Now that way you don't have to memorize any sort of formula. You just say, hey, Kelvins are never negative because it's an absolute scale. And so then after you figure that out, yes, to go from Celsius to Kelvin, you add 273. And to go from Kelvin to Celsius, you subtract 273. And you can't go below 0 Kelvin, and you can't go below negative 273. So if we go, all the way to the bottom here, maybe do a little broken line means I can't fit it on the page, right? The rock bottom of temperature is negative 273 degrees C, and the rock bottom of temperature is 0 Kelvin. All right, Kelvin, because it looked like okay. And then you notice something? A lot of times we use temperature changes. So if you were to go and heat something from freezing point of water to the boiling point, that would be a change in 100 Celsius, and the change is the same in Kelvin. So one thing I really didn't say in the beginning is Kelvins and Celsius are spaced the same way. The difference in a degree Kelvin, or I called it a degree Kelvin, whoops, that's a difference in a Kelvin and a degree Celsius are the same thing. So if you heat something up and it increases by 18 degrees Celsius, it also increases by 18 Kelvins. Okay, folks, that's all you need to know about temperature. Sure, Fahrenheit, there's some sort of 9/5 things and 32 degrees, but we're never going to see a Fahrenheit in the first place. So we'll just go straight to Kelvin or straight to Celsius. And sometimes you need to use Kelvins. Sometimes it's an option whether you use Kelvins or not. But those are the two scales we'll talk about this semester, especially about halfway through the semester when we do thermodynamics and thermochemistry. Okay, on to something else. Okay, here's my something else. My something else, remember in the last video I said one way to, if you're good at unit conversion, you'll never get ripped off. And so this is a box of hand sanitizer. I should have covered up the brand name because they're not sponsoring me in any way. As a matter of fact, a little story about this box of hand sanitizer. I think these are like refills for public restrooms, but my dad found these at a dollar store, an independently run dollar store, and for $1. Boy, that'd be a great find now, and he gave it to me, by the way, when I went and visited him. Thanks, Dad. He's probably not watching this. But it says here 2 liters. So, is that true? I don't know. We're scientists. We're skeptical. I know that, by the way, there's 1,000 milliliters is 1 liter. And a milliliter is the same thing as a centimeter cubed. All right, so that's what we're going to do is I'm going to go and take an instrument. This is what we call in science a ruler, and it has centimeters. So what I'm going to do is I'm going to take length times width times height, and I'm going to see if this thing really is holding a liter. And I'm going to do it really quick and dirty here. I'm not going to, hey, next time we'll talk about being persnickety with measurements. So that was 21 and a half. 21 and a half. I don't want to write on the hand sanitizer bottle. 21 and a half centimeters times 12 and a half times 9. That's going to be our volume. So what we've got is cubic units here. And you have this thing where we're going to then convert to milliliters. But hold on, let me do this. 21.5 times 12.5 times 9 is 2,418.75 centimeters cubed. Centimeters times centimeters times centimeters. And it happens to be that that's the same as a milliliter. We'll talk more about that in the next example. And there's 1,000 milliliters in a liter. So 24. And then you know what? I'm not supposed to include all these digits, but you know what? We'll talk about that next time. I'll commit a faux pas today. 1,000 milliliters, 1 liter. So that's really, and you know what? 10 to the 3, but okay, I'll let it go today. 2.41875. Let's talk about that actually. Let's say that I measured that to tenth, you know, and then I could say that's 2.4 liters. My units of milliliters canceled, and so that box has a volume of 2.4 liters, and so the outcome of that calculation is that apparently the box is bigger than the package inside. There's like a little plastic sort of bladder in there, and so I did not get ripped off, mostly because my dad gave it to me for free. But my dad didn't get ripped off in terms of the volume of that. But you do look at these square containers. Oh geez, do I dare show you guys this one? Huh? You look at that and you think, is that 5 liters in there? Yeah, go measure it. It's just that when they're square, they take up their good use of space, and so they can be deceiving. You'd say, does a 2-liter bottle fit into that thing? Yeah, you know, it's wider and deeper than a 2-liter bottle. Okay, next example. This, sometimes I can't make these relatable for everybody, but if you're a gearhead, you know that one of the ways to measure the displacement, or how, you know, sort of powerful your engine is by volume. So, you know, nowadays it's in liters. In the old days, it was in cubic inches. And so what you got going on here, folks, is, you know, we're getting away from, I was kind of saying that we're a little behind the times last time, but we're not completely out of the, you know, SI kind of system. Nowadays, if you buy a car, they'll tell you it's a blank liter engine. I used to drive a Honda CRX. It had a 1.5 liter engine, which is one step above a sewing machine. It did not have much get up and go. This thing would be like a Chevrolet 454 big block, and that has a lot of displacement. That would be, we'll find out how many liters it is, how many times my CRX it was. So here's how we're going to do this, folks. Do you notice that they gave us this conversion? And that is because, and let me show you what not to do. So over here, I like to do what we call the wrong thing. It's like a corner of shame. And the wrong thing to do would be to just use that conversion once, because inches cubes don't, let me just show you. I'll set it up, I'll say, hey. And then I could say, okay, I'm going to use the conversion factor like Mike did in the last time. 1 inch, 2.54 centimeters. And then I could say, well, the answer must be 454 times 2.54, and then 1,153, which would be 1. Centimeters. By the way, that would not be units of centimeter. I could say wrongfully that would, centimeters cube, oh, that's 1.15 liters. Well, that's less than my Honda CRX used to be. So that would be the wrong thing to do. What you really need to think of these cubic units as is that's really inches by inches by inches. So this is a big old cube. we're going to convert it to centimeters cubed. And a centimeter cubed is centimeter by a centimeter by a centimeter. So if you use the conversion once, you've only converted one of the dimensions, and that would be the wrong thing. So what you do is, I just do it 3 times. So and it adds a lot of clutter, and it doesn't feel very sophisticated. But I could say inches, and then I say, hey, that's really inches times inches times inches. And so I'd have to do this 3 times. That's the only conversion they gave us. There's another. So you'd say, oh, 1 inch, 1 inch, 1 inch, and then 2.54 centimeters, and 2.54 centimeters, and 2.54 centimeters. And now look what happens. Inches cubed are canceled by inches times inches times inches, and this would have units of centimeter cubed. Still haven't solved our problem yet, guys. So hold on, gang. Let's get this done to times 2.54. Times 2.54, and this would be, I don't think I did it right, 454 times 2.54 times 2.54 times 2.54, and this would be 7,000. We're not done yet. They want it in liters, folks, so just hang in there. So 7,439.7 centimeters cubed. So I'm going to be very verbose here, but I'm over-explaining, but I'd rather do it that way. 1 centimeter cubed is 1 milliliter. I was supposed to say milliliters. I smudged myself there. 1,000 milliliters is 1 liter. Cancels, 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 cancels. This would be 7.4397 liters. Then we have this, folks. Next time we're going to talk about significant figures, but the bottom line is if they give you 3 digits, your answer should have 3 digits. I'm going to call that 7.4, and then I'm going to round that to 4. 7.44 liters. That's a big old engine, by the way. My Honda CRX was 1.5, so that would 2 of them would be 3. That's 5 Honda CRXs. Of course, they probably have gotten more efficient, so it's not like, this Jimbo's car would really make an easy time of mine at a stoplight drag race, which you should never do, by the way. Let me change the subject before I get in trouble. Folks, I'm going to end today with a little bit more preaching about units. What's going to happen is we're going to need to solve this, and we were given 2 numbers. And someone, you folks out there, I've met you folks for 27 years. There's often people who are really smart, but this is where I try to take the smart ones and I try to not make an example of them, but I just try to make them see the world from a different perspective. Because the smart folks will be like, hey, I see density. And I'll be like, okay, how am I going to solve this? And they'll be like, well, D equals M over V. I'm sorry, I'm trying to sound like a smart person, but I'm just sounds like I'm mocking people. But I'll be like, how do you know that? And the person will say, well, I memorized it. It's the formula. And then, sometimes, folks, I can tell you that I have seen, I'm going to make the wrong thing. I've seen this before. I've seen that before in my career. I've seen it I've seen it too many times. What happened there? Well, I memorized it. Yeah, you memorized it wrong. Because, it's not like something that's really all that exciting. Sometimes you just memorize it wrong. 862-9756, that was Julie Franklin's phone number in 1988. I wanted to memorize that. But this isn't as exciting as that. Julie Franklin drove a Dodge Dart, by the way. Back on subject. So what's going on here is there's only 2 things. Well, you can't add or subtract these numbers. So let's just take that out. There's only 3 things I can do. Now, why can't you add or subtract numbers, these numbers? They're different units. You can only add or subtract numbers with the same units. So the bottom line is we're either going to multiply these or we're going to divide them. There's only 3 things you can do with these numbers, and I need to get the answer in grams. So I'm going to do 3 things to these numbers. I'm going to divide 0.795 grams per milliliter by 250 milliliters. I'm going to divide 250 milliliters by 0.795 grams per milliliter. Or I'm going to multiply doesn't matter what order you multiply, thanks to multiplication is so easy like that. Multiplication's pretty chill like that. And I'm not going to even do all those calculations because I'm going to go figure out what the units are first, and the one that gives me grams is the one I'm going to do. So what would be the result here? This would be grams divided by milliliters divided by milliliters. This would have units of grams per milliliter squared. You know what? I ain't doing that one. That's the wrong thing to do. And you can kind of tell, you say, hey, the density's about, after you get good at density, you say, hey, this is a little bit less dense than the water, so that it should be in the neighborhood of 250, not crazy different like that would have been. Just like this. This would have units of milliliters. 1 over milliliters would be milliliters squared per gram. That ain't it. But if I multiplied them, milliliters times 1 over milliliters would cancel. I would get units of grams. And so I didn't really even need a formula. I didn't need to memorize the formula. Sure, I've memorized that formula. I've seen it a gazillion times. And then this would be 198.75 grams. And then, I would need to round this to 3 digits because I had something with 3 digits, so we'll call that 199 grams. And that would be my right answer. And, now here, our formula is bad? No, it's okay. But then what I'm really saying is that the units, if you pay attention to them, will keep you from doing it. I'm telling you that somebody would maybe do that thing, not this one, but somebody might be tempted to do that. You say, D is M over V. And then they get kind of carried away on the way to figuring out, what M is da-da-da. You do this business and you'd stop there, but sometimes people would divide. So the units are a way to keep you honest. And to be honest with you, I didn't even need to know a density formula to solve that. I just needed to get the answer with grams. And a lot of times the units aren't going to be as relatable as grams and milliliters, but you can always, if you just stay disciplined and make those units a little tag that goes along, inseparable, the units are like your friend. These calculations are dark and scary sometimes. It's like going in a cave with bats, but the units have your hand. They're holding your hand saying it's going to be okay, and there's light at the end of the tunnel. I think I drank too much coffee today, guys. But we'll see you next time where we're going to do a density experiment with Mike's magic cubes. I'm trying to make that exciting and tempting for you to come back next time, which you should. See you then. Adios, amigos.